I'll skip that slide. Open problems. All problems in bioinformation theory are open, including any that I may imply have been solved. What is memory? How is it physically stored and accessed? There's memory and there's learning. I think learning is rather well understood. And learning is, it's a complicated area, but just sort of what learning is understood. It has to do with adjusting all these weights of all these connections among these neurons as a function of experience. And that's how you learn, how you adapt in some way to do that. Chip Levy tells me that memory is the same thing. I don't buy it. I don't know. I think memory is deeper. And that there's more to the mechanism of memory than just that. Somehow, we all have this memory. So if I say to you, Humphrey Bogart, there pops up in your mind a picture of Humphrey Bogart. It's not as sharp as the pictures of the people that you're sitting next to that you look at. It's not like that. But it's pretty good, you know. It's a more than just a computer icon level thing. And not only that, but I can tell you a lot about what it looks like. It's not front on and it's not sideways. It's this way on an angle, and there's a cigarette hanging out of the mouth and there's a hat on. Probably comes from the Casablanca poster or one of them. But you have it. And the question is, where was it? There's also a question of how did you call it up, but I'm less concerned with that one for the moment than where was it, in what form? Damn well is not stored like a bunch of JPEGs on your computer, that's for sure. Too many of them for that to be true. It's just not true. But I don't know what is true. I'll skip this also. Are there any experimental results? Yes, but not from really of the above. I want to talk about this experiment to which I alluded by Bielek and others, in which they calculate the Shannon mutual information between a stimulus that they generated and a response that they measured from a fly. So this experiment worked something like this. They got this fly. They pinned it onto a piece of apparatus because they would much rather have recorded from a moving fly, but that was not very possible. So they pinned it onto a piece of apparatus. And then they took this grating, the certain spatial frequency there that's shown on the top, and they moved it back and forth in front of the fly, where they recorded, meanwhile, spikes and non-spikes from a certain region called H1 in a fly, which is something like V1, I think, but it's an ordinary house fly. And they got a sequence of zeros and ones. They moved this thing according to some Gaussian random process with stationary memory in it. That's some kind of spectrum. They moved it around like that. Then, let's see if I back it up. I think it goes too fast on this machine. Okay, then they did it again. Moved the thing again with a new sample function from the same stationary process, but not the same one. Well, actually, no, excuse me. First they moved it, but they kept the stationary, they kept that particular realization of the random process, and they repeated it 300 times and measured the different spikes that came out. And after they did that 300 times, then they went through a very large number, I don't know how many hundreds or thousands of repetitions 300 times of different such realizations of the stochastic process for moving this grate. They picked this thing in such a way that they felt that it's something like what the way they see these fly movements, and they tried to keep the fly's interest in this, because this whole thing took 9 hours with the fly spent down there. They got 3 hours of rest during the 9-hour period, and these things were being recorded. I don't think it got released, though. It was pinned to the apparatus the whole time. Probably not with a tack that big. They averaged over many such representative stimulus things, and in that way they first were able to compute the conditional entropy of the response, which is all these ones and zeros, given that the stimulus was some particular little s, because they repeated that the same one many times, and then they averaged it over the one that they repeated in such a way that they finally really found the averaged conditional mutual information rate for this response of this fly to this kind of thing. Okay, it's not the real thing that the fly sees out there in the world. That doesn't really matter. The point is that they put a stimulus on it, a statistical stimulus on it, and they calculated the response. And so now, when they get all these response things, they can go and they can calculate the entropy given a particular value, little s of this stimulus, the average of that over all these things, which is the mutual information, the conditional entropy of response given stimulus from this ensemble of things, And then they also, of course, could do the old-fashioned thing of simply computing the entropy of everything that came out. And now they had H out and H out given what came in. And subtract them and they get the mutual information. What they found was that it was about 7 bits of information per, I believe it was second, and this stuff, 7 bits a second worth of information. But more important, well, of entropy rate, excuse me. And of the 7 bits of entropy rate, 4 of them were mutual with their stimulus that they were putting on. And the other 3 were who knows what. Just stuff that is noise or whatever it is. You know, but finally, somebody figured out, it's painful, how to measure the neural information response, the mutual information to a response on a part of a neuron, so that they could find out what was the information rate between what's coming out here in this spike train and the stimulus that you were putting on in your experiment, as opposed to simply measuring the entropy of the output spike train. It's a big breakthrough and very important. Deal like it all behind that. At least I feel it's very important. So my time for the first lecture is up. There's no better way to end it than to put up a picture of the man. Do you know why this picture? Well, first of all, we'll have to practice how to hold our head in our hand. And you can't do it like this or like that. And it has to be like this. You have to hold it. That's the way that thing. But you know why that's the way he held this? Well, I spoke to the sculptor about this. Jack Wolf and I had a discussion with him. Picture came from the guy who took this thing very seriously and handled it. Many pictures of Shannon that he studied from different angles and so forth in order before he made the statue. And this one that he had here, this thinking pose, was the one he liked the most. But what was happening over here is a cigarette. Okay, so we'll continue after a break.
I'll give it to you in just a second. Yeah, exactly. So there's handouts for the second lecture. So those of you who don't have a handout, just please put up your hand, and then we'll get you a one of the handouts.
There is a way to do it with that.
And Ye also has an announcement about the poster sessions.
Yeah. For those of you who is going to do your poster session today, if you didn't submit your poster, you can give it to me after the lecture, and I will be in the front of the classroom.
Okay, so make sure to take care of that. Another thing too, after this lecture, we have a little bit of a shorter lunch. It's only an hour today, and the panel will be in the IST Cybertorium, which is kind of in that direction. But I think you have it on your maps, so and we'll be around, so I think we'll find the way. So after that, let me get you hooked up again.
You're wiring me for sound again here, huh? Okay.
You see it on? There you go.
Okay. Well, you tell me when to begin. Do I just begin, or okay? This is on. Well, now I'm going to try to show you, because you're information theorists, a proof of what I call the main theorem in the previous thing. Unfortunately, it's not on small slides. I understand that there's some way that they can send this to those of you who have laptops in front of you, because they have it. But I will. Okay. So there's a preprint that my former student Yu Zhang Ying and I have submitted to IT Transactions, called Feedback Capacity of Binary Channels with Unit Memory at the output. But I'm not going to show you that whole thing. I just selected about 5 or 6, maybe 7 pages from it that I want to talk about.
So this is different than their handout, though.
Yeah, that's not that handout. That handout's coming later in the talk.
Okay.
This is the proof of the theorem from the previous talk. Yes, this is not that one. Okay. I'm going to get to that one, I hope. Okay, so we look at a channel which is in the middle of that channel box. It says P of yk given xk and yk minus 1, and that's the kind of thing that I had when I drew the vectors of y's were in that case vectors of binary data from some neurons in a region, and the conditional distribution for what would come out next depended on what was coming in, a vector of binary inputs of zeros and ones, and what the previous output vector that got fed back across to the neural region itself in the manner that was depicted was. And so the channel from one time instant to the next remembers, it's a channel with memory, but the only memory that it has is what the previous output was. Output is a vector, really, and it doesn't remember anything else about previous inputs or previous anything else. Well, information theorists would like to say that if you have a channel like that, you build an encoder and a decoder, and you have some message source, and you try to figure out how to take your messages and encode them in the right way through this encoder to get them in the input alphabet of the channel, and then use the channel for some period of time and make decisions as to which of the messages got sent, and there's some W hat. And if the exponential rate of growth of the number of the messages that you can distinguish with high probability over a long period of time is in fact growing exponentially, and you can make it grow at some rate R, then that R is less than C, and if you're really good about it, then the maximum such R is C, if you can figure out what that is, let alone figure out how to transmit at it. But that would be the problem that the information theorist would view when given a channel like that. I don't think the brain cares about that problem or even knows that that problem exists. It's not the problem of interest. And yet, of course, it solves it in some sense, but it doesn't, it's not the problem, really. That is to say, if it's the problem, then somebody should be able to show me where the encoder is and where the decoder is, and I can guarantee you right now that they can't do that. So if it is there, I mean, in some sense, maybe it is network-wide in some way, but nobody knows how to point to it. It doesn't work like that. It works the way I showed it on the other slide, that last time's output comes back, it gets fed in, inputs come from elsewhere, and the next thing simply gets produced, and then it happens again, and then it happens again, and then it happens again. And you can't point to the encoder-decoder box, because I don't think it exists, because I think things are matched already, so you don't need it. Right? That's what the double matching part of the talk earlier, or at least the matching to the channel that I was talking about in the earlier part of a previous talk was about. There really isn't an encoder and a decoder in the information theoretic sense of the term. Certainly not a block coder. Probably not a sliding block coder. Probably not a convolutional coder. Not all our favorite things. Something else. But the channel is there, and the channel is used efficiently, especially, I think, in the energy sense. So here it is in that little thing that's called equation 1, and P of yk, given all the x's before and all the previous y's, and the initial y0 just becomes P of yk given xk and yk minus 1. So that's this unit memory at the output. Okay. So given the initial, given the channel state yk minus 1, the current output depends only on the current input and not on the earlier inputs and outputs. And now, what I said was that we're going to, okay, let's see, trying to figure out how to, what to bother to talk about and what not. There's some material about here about whether a channel has feedback or not, or whether it uses the feedback or not, and maybe I'll skip that page. Try not to have to dwell on that one. Okay, there's some stuff at the bottom of this page that has to do with so-called directed information. Massey's directed information as opposed to Shannon's mutual information. There have been some studies by Jim Massey and by Tataconda and a few others in the group that Tataconda was in at MIT. And they seem to show that, in general, if a channel has memory, let's put it this way: the fundamental theory of information theory that that the capacity is the maximum possible mutual information rate between the input and the output, subject to certain constraints that may be imposed on the input usually, isn't necessarily the capacity, but it's just an upper bound on it for certain channels that have memory. And Massey introduced and Tataconda tried to prove a converse associated with this to show that you really want to use Massey's directed information, which in the case of the general kind of channel with feedback is the right thing to use rather than Shannon's mutual information. And Massey's directed information is always less than or equal to the mutual information rate. And so that if you're dealing with a channel with memory, you may have to not look at regular Shannon information, but rather at directed information. Fortunately for me, it turns out that if the nature of the feedback is that you feed back to previous output, and that's the only nature of the, and you do it in this way that's in keeping with the equation of P of yk, depending only on xk and yk minus 1, and not in any of the other earlier things, then it turns out that the Massey, the way to distribute the input in order to maximize Massey's directed information also maximizes the Shannon information, so that for that class of channels you don't need to distinguish between these two things. So I don't want to go into that here, but that does happen. So it doesn't matter really, at least for this class of channels, whether you adopt Massey's view of what has to happen there or whether you stick with the usual Shannon information. So there is something here about directed information. The definition of it is down there in that equation on the bottom. Is I of xn and yn, but instead of there being a semicolon in between them, or an up caret that the Hungarians like to use, there's an arrow that goes from x to y to tell you that I'm looking about the direction of the information transmission from the x's to the y's. And then the thing that's over on the right-hand side here is the sum of a bunch of terms, and these involve mutual informations of the Shannon type conditioned on previous outputs in a certain way, so that anybody who's interested, I can point you to the Massey papers about that. It's still somewhat controversial, not Massey's part of it, that shows that this thing is always less than or equal to the mutual information, and that you can send at rates at least as high as the maximum of the directed information. The controversial part, I don't know if it's still controversial, but it seems that it is this converse that says that it's in general for large families of channels with memory that there's no way to do better than the directed information rate. And you can't send things higher than the maximum of the directed information, which in general is less than the maximum of the Shannon information. And there are examples of where it's known to be less, but the proof of that converse, the validity of that, seems to still be in question in some people's minds. But fortunately for the problem that I work on, it doesn't matter the model that I have. Okay. So what we want to do is we want to maximize, let's say, the directed information starting at some y0. It's behind the conditioning bar on the top equation. And I want to maximize the mutual information rate between the x's that get put in between times 1 and n and the y's that come out between times 1 and n. And I want to maximize that over for the moment, let's just say all ways of distributing the input, and don't concern yourself yet with any kind of constraint on it, such as some sort of energy constraint. Energy constraint, by the way, doesn't just come from the input, but it also comes, in fact, more from the output than it does from the input, because the outputs are the spikes, and the spikes cost more energy than the processing of the inputs to decide whether or not to make the spikes. So when you do put energy constraint on it, it's not just on the input, but it's on the input-output combination if you do it right. Okay. Let's see how I would go with that. Okay. At the bottom here, on this part that I'll point to with my pointer, because I know you can't read this, especially from the back of the room, very well. It says, what we're now going to do is define another set of input distributions for xn. And that's called P star of xn. And what happens in P star of xn is that the conditional probability of the next x, given all the x's that came before, and all the y's that came before, and y0. This is the next x, not the next output. That describes the channel, not what the probability of distribution of conditional distribution for yk is given these things, but for xk, given all earlier x's, earlier y's, including the initial one. If you restrict that to be of the form that it depends only on xk, only on yk minus 1, so that you've built yourself a Markov chain condition that looks like this. You have this xk. This thing is really so that yk minus 1 screens xk away from all the things that went in and came out before that. This is not necessarily true. It's certainly, in fact, not true of all ways in which you could decide to put an input into this system. But it turns out that if you put this requirement on, you will find that in this family of the thing that maximizes, let's say, the Massey information rate over the original entire P of xn that you were maximizing over here without the star in it, that the optimum in this set will occur for a member of P star. Maximum happens in P star, in this model. That when you go to look for how to distribute the input so as to maximize the Massey mutual information rate between the x's and the y's, you will find that the maximizing thing meets this restriction. Yes?
Sorry, just a question on the Markov chain. Shouldn't the last y be between 0 and k minus 2? Because k minus 1...
Oh, well, I put it there, but I guess it's not necessary to put it there. Well, it's true the way it is, but of course you could knock that down to k minus 2 if you wanted. But, you put that on the other side, it's obviously this screens this away from itself. So it's not wrong to do it, but it isn't necessary. Yeah.
So you're saying that the optimal feedback only needs the most recent output and not the long history. Is that what you're saying?
The optimum thing to put in, right. I mean, you can think that that's the way the brain ought to operate, because it says, well, I got to put something in now. What is it that I remember? I've actually really thrown away all the old stuff. The only thing that's still there, in terms of, is the most recent thing that got fed back and went into my synapses, so to speak. And the rest, I don't really know what happened to that anymore. I don't have it. I need to produce the new input at this moment. This is the only thing about the past that I know. I don't even remember what I put in myself. I mean, we think there's an encoder remembers the whole past of all the inputs. Nothing like that. Nothing remembers the past. But it generates the right input anyway. What?
I'm a bit confused. So,
good.
On the other hand, you say the brain doesn't have an explicit encoder. No, but this particular problem that you're looking at has an encoder, right? So I'm a little bit confused about the issue.
Well, it makes a statement about the way in which the input is generated from things in the past. That it says that of all those things in the past, the most recent output is the only thing that it depends on.
But in this model, you build that into the channel itself, right?
No, this is not a statement about the channel. This is a statement about how to distribute about a family of input distributions to that channel. The channel model is stuck there at what it was. P of yk, given all the stuff in the past, depends only on yk minus 1, and it depends on xk, what you put in now.
And yk
So,
minus what?
yeah, yk depends on xk and yk minus 1 and not any earlier x's and y's. This is a statement about how xk depends on certain things in the past, which is not, of course, true of all ways that you could put inputs in. But you can look at the subclass of inputs that have the property that what goes in at time k, given all these earlier things, depends only on yk minus 1 and nothing else that went in or came out earlier than that. Okay? And when you do that, you find that the maximum of that of the Massey's directed information rate through this channel model occurs for a situation in which the xk's and yk's are related such that that thing is satisfied.
Yeah, I understand. I think I understand the mathematical statement.
Okay, yeah.
My question is a modeling question.
Yes.
So you're saying that when you define a channel, which is that the output at time k only depends on the current input and the past output, is that a model of the brain incorporating the feedback that you're assuming the brain is doing, or is it a model of something else?
Well, it's a mathematical model, but it is hoped that it captures the spirit of the way in which a brain region works. Yes.
With feedback.
Brain
then
regions.
now in this problem, you're on top of that talking about feedback,
Yes.
right? So that's what I'm confused about.
I'm still, yeah, well, what I'm trying to do now is to figure out okay, so I'm not really interested in figuring out the numerical value of this maximized Massey or Shannon information. But what I am interested in doing is characterizing the nature of the processes at the input and the output that maximization of it that are true of the process that once I pick a process at the input, then the channel will determine how the output is jointly distributed with that if I put it in. And I want to know what is true of the joint input-output process. Is it a Markov process? Is the output process Markov? Is the input process Markov? But which process am I talking about? I'm talking about the one out of all the ones that you might pick that maximizes the directed information rate. Subject to the constraint that I want to put on, which I haven't put on yet, that the energy is constrained at a certain level. The way I'm going to get around this energy thing is the following, that I'm going to show that for any process that you give me that is not necessarily in P star, I can make up another process that is in P star that uses the same amount of energy and gets this mutual information rate at least as big. And so in that way, I actually get it for the constrained channel, but that's a little further downstream. But I'm less interested in that, really. And it's not that I'm interested so much in the number, and I don't know that I ever really even tried to compute the number that would be this Massey or Shannon information capacity. I want to know what the processes are like that the brain puts in there. If the model is true, I'll call it the brain, but if the model, what the brain model would like to be there in order to get the most information through for a given amount of energy. I'm going to study those processes. Yes?
What are you associating with the encoder, and what is the channel for you? What, in terms of this the brain model that you're thinking of, what is the channel? Which part is the channel, and which part is the encoder?
Okay.
In your model?
Well, the first part of that question I can answer. The channel is the picture that I had on the board before. It's all these neurons in a group together, interconnected, and receiving inputs from, which I have to maximize over here in order to get this thing, from above and below, regions above and below. Those are the inputs. And then there's all these connections of those inputs to synapses on all of these different things in this region that I'm trying to find out this maximum information rate between all of its inputs and all of its outputs. Okay. Now, what is the encoder?
Is that the feedback?
Yeah, I don't really...
That's the mapping.
The encoder is hard to point to, because what the encoder is something that somehow picks the right XK to stick in next. And it comes from the whole brain in some complicated way. So I guess my only way to answer that is the encoder is the entirety of the rest of the brain, other than this region. because I don't know how to say less than that. Although really, you could say that any part of the brain that doesn't have a direct connection, any neuron in the brain that doesn't have a direct connection to this thing is not in my encoder at time xk to produce xk, because it can't get there. But the other stuff is really changing what those are going to be by time k plus 1 comes about. So really the only way to safely say it is that in some way the whole rest of the brain produces xk. And that's not just the brain that does it, but it's also the stimulus coming into all the sensory organs from below at that time and coming up the chain. All of that, plus all the stuff that's getting fed back. It's the whole rest of the world in some sense. Yes?
So somehow your channel is what's producing these energy-constrained outputs, right? So
I'm constraining only the energy in this case, this region that I'm looking at of a bunch of tightly connected neurons. I could have done this for 1 neuron or for 10 neurons, but I guess the way when it's useful here is that it's also true of 1 neuron or 10 neurons. You pick any group you want, but it's of interest really when they're tightly, they have a high degree of connectivity among themselves, so there's a lot of this feedback.
Now my question is, the channel inherently constrains the energy. Do you have to add an additional constraint to model the channel correctly?
No, I mean, I don't put the number on. I just say that there's an energy constraint. Yes, I agree with you. The channel has a certain way of putting energy into the processing of the X's, because those that it doesn't fail when there's spikes when they come there, it uses energy up to push stuff across the synaptic cleft to start building up this postsynaptic potential. It uses up a certain amount of energy, which is sort of not really important in the calculation, just to metabolically keep everything alive, but that's a constant rate, so it's sort of not interesting. And then it uses a heck of a lot of energy when it finally does send spikes to propagate them. It's not so much a question of sending them, of creating them. It's a problem of propagating them down the axon, because they kind of get created by sort of a spring action. It's like when you're pushing this, somewhat analogous to pushing a spring all the way in and then releasing it at the moment that you send it. It doesn't take any energy to release it. You pull the thing away and release it. But then you got to send this stuff to 10,000 places, and that requires all kinds of energy going into the way in which you propagate that to all the places that it has to have. So I count that energy against this group. I don't count the energy of the spikes that arrived, because that was done by a different group, or at least or by this group previously. But what happens here is that if you put yourself in this in this set P star, that you find that the distribution that maximizes the joint distribution of the inputs that maximizes, let's say, the Massey directed information rate from those inputs to the outputs that get produced over time, the rate of that, satisfies this condition that's on the board here. It's not just something that says that the outputs and inputs are connected according to the channel, but also you can put on the additional consumption restriction that this has to happen, and then when you do that and you look at what comes out, you find out that when you put that together with the channel equation, that the distribution of xk and yk given yk minus 1. Oh, okay. There's one that in the class of P star, given any distribution, not necessarily in P star, there is a distribution in P star which has the same or larger directed information from x's to the y's and uses exactly the same energy. Because the energy is an instantaneous thing that's simple. It just adds up from one instant to the next. The information rate, as we know, is complicated, because you can't assume that things are necessarily independent from one instant to the next. But the energy, you just add it up. All you need to have, the energy to work right, is that the joint distribution of xk and yk given yk minus 1 is the same for the element in P star that you're associating with the element that was not necessarily in P star. If you keep that distribution the same, then no matter how you measure the energy is the same. In fact, it doesn't even have to be energy. Whatever the function is that depends only on how an xk and yk are distributed given yk minus 1. Or at the beginning given y0. So I call it energy, but it really could be something more. I think of it that way, and I do think that's what it is, but it could be anything else that really is something you're constraining that depends only on how xk and yk are distributed given yk minus 1 at time k. And that'll determine the energy at time k, and then you step along in the next one. So if that holds for every k, the energy is the same. So maybe I should just leave the argument at that because it's going to take a long time to try to do these steps. Maybe the point here with a group of information theorists, since you're going to get this paper anyway, is to see that you can formulate the theorem. Maximum directed information is attained in P star. That's in the middle of this line. This is theorem 1. The maximum directed information is attained inside P star of xn, and moreover, for all xn and yn in P that are distributed according to something in P star, the yks are a first order Markov chain, the xk yk pairs are a first order Markov chain, and the xk's are not. And you've all seen that joint Markov chains with one component can be perhaps Markov. The joint thing is Markov, and then if you take one of them, just say just xk, that's a function of a Markov chain. You take just yk, that's another function of a Markov chain. Functions of Markov chains, instantaneous functions of Markov chains are not necessarily Markov, but in this case yk is and xk is not. And that's the way it comes out. So all this stuff gets proved here by kind of, in some sense, it's the thing that I least have to talk to you about because it's the piece that you can sit down and read with your background. And you can agree with it or not. Whereas the other stuff here is the bio, and this is the math. So it does go on like that for a few pages. And what's this last one? I don't remember. Yeah, this is the last part is the optimum input process, and it's not necessarily Markovian. It only got bigger on this slide because I truncated the top and the bottom of the page since I didn't need the bottom, which was most of it, and then PDF made it big, but the others are smaller. So I think I'm not going to take the time to do it because I've posted this and it'll be available. They can download it into their machine and you can read this thing.
Not right now. We put the other one on, but we'll put this one on the web page too.
Yeah, sure. I'll give it to you. It's just called proof of the main theorem equals theorem 1. Okay? And in some sense, this is the least of what you really need to see here, except to know that it exists. Okay? Yeah. Yes?
So this is a general question about the modeling again. So we are making some kind of a matching. And at the end of the day, the system behaves like autonomously. It uses the feedback, the previous channel output, and gives certain output. And I couldn't see anything like at the end of the day, a probability of error or a probabilistic measure. Like, why don't we use, for example, classical like system theory approach and do a matching there? Like, why it's better to do it this way and talk about direct mutual information rather than a Kalman filtering? Like, probably I totally missed something. But
I think I understand what you're asking, and maybe I'll try to rephrase it and you tell me in another way. You tell me if I'm close. Okay. I think you're asking why you're just trying to maximize the information, subject perhaps to some energy constraint, instead of putting into this thing the real problem that the brain faces of making decisions and trying to minimize some kind of Bayesian or whatever cost on the decisions. It could be an error frequency criterion, or that would be like an ideal observer, or maybe some more cost-weighted thing associated with different sorts of errors that could be made that would be more Bayes optimum or something. And why don't I have that decision? Because that's what the brain does. It makes decisions and takes actions in the world, and we want to know what fraction of the time it makes the right decision and not just look at this information. Is that the question?
Yes, that's my question.
No.
Yes, that's my question.
What?
Yes, that's my question.
That's your question, but you have a different question. Well, okay, I'll answer your question, then we'll try to come back to your one again.
I think it's also his question.
Okay. I don't know how to solve a problem, and nobody knows how to even formulate a problem that's anywhere near as complicated as what you're talking about, that not only involves the brain, but then the actions that are taken and the feedback that comes from the result of those actions in the real world back in through the senses in the future. That's dependent. You have to model not only the brain, but the whole world to set that whole problem up. Okay? That's one thing. The second thing is that I do think that even inside the brain, and even at the upper levels of the visual cortex, for example, this decision gets made. People even know where in the brain the point is between, the point or points are in the brain between what you would call purely sensory processing and what you would call motor processing, in the sense that you make a decision which is a decision other than not to decide yet. In other words, to take more data. I won't quite call that one a decision. It's sort of a sequential decision process. And at a certain point, you take a decision, which really means that you take an action, which means you move something. You do something motor. The decision is really motor eventually. It's many levels above what I'm talking about. And it's very hard to try to formulate it. What's being postulated here, and it's a postulate for sure, is that in the primary visual cortex, when you don't yet know what it is that you're encountering visually and with the other senses, you just gather up these inputs and push this information up the chain as fast as you can toward the place where the decisions will eventually get made. You're not involved, this thing here is not at all involved in making decisions. It's involved in gathering information, pushing it up. That's what I believe is happening. So that's why I don't put a fidelity criterion of a distortion type onto it at this point. In some sense, this is the rate distortion theorist talking. The rate distortion function is a straight line because the thing that you're trying to maximize is information. You want to know what's the maximum information I can get for a given amount of information? Well, the answer is that you can get that much. Yes?
How do we know that the quantity that we are pushing up by doing this is actually the relevant information for the final decision?
How do I know that this is relevant?
Why are we assuming that this directed mutual information is actually the quantity that will be useful at the bigger system at the end of the day?
Well, I don't have a good answer. Okay.
Do we have a reason to believe this one is better?
Well, it's a question of natural selection. If it weren't, then something else would come along to be built that used the information that was available and the energy that it took to do it more efficiently than this, and this would be the species that would be there now instead of the one that you just described, and that's why it's not that way.
Okay, so we do have, you say, empirical information, like...
Yeah, it's just postulated on the belief that healthy systems are nearly optimum at what they do. And optimum here means that they, at the lower level, means they gather information for the least energy. In higher levels, that information, if it isn't the right information for the decisions that need to be made, then this organism is not going to stick around for long. And it'll be replaced or modified or move over into one that does gather the right information for that energy.
I understood. So we have enough experiments to suggest that this is actually the thing that is pushed off.
Yeah. It's based on some belief in natural selection in a very high degree. I guess why I would say that this is a worthwhile formulation, even though all it's doing so far is gathering up energy, information for energy. It's doing some kind of trade. We're kind of assuming here that it not only does that, gets a certain amount of information, but that it gets in the main what you would call the right information for the problem or problems that it's trying to solve for that amount of energy. Because if not, it better adapt itself to learn how to do that, or something else will take its place. Yes?
So basically, by not putting this any fidelity requirement and are you assuming inherently some sort of separation by looking at this? You're saying some information is transferred to the upper layers, and at this point, you are not really looking at any fidelity requirement, right?
Well, I'm absolutely not looking at the decision problem at all at this point. If that's what you're saying. No, not at all.
Does it inherently correspond to some sort of separation?
Yeah.
Basically, this channel coding and whatever we can call it source coding.
Yeah, I certainly haven't closed the loop on this thing around the outside world to see the effect of decisions. So far from that, and actually not even up at the point where you make the decisions. It's more primary. It's kind of a model of primary cortex, with the view that what primary cortex is about, at least for several steps up, is just to gather information about what has been coming into the senses and send it up the chain where it gets processed a little more and more globally, instead of just whether or not there's a change in intensity on this particular in the horizontal direction as I move through this vertical line. Those are, I only get beyond. But you do gather that kind of information. You send it up, and then you get some lines and other stuff, and it gets a little more complicated in B3 and B4. But it's still very, very far from decision making. I don't think it's yet referenced anything about what you've seen in the past. It's all happening autonomically. It's not even trying to compare it with any pattern that you've seen in the past so far. This is in the first tens of milliseconds after some stimulus has been put on for you to look at.
Can I have a quick comment? So if you look at 1948, Shannon paper,
Yes.
he says, here's the problem, the communication problem, and here's the simplest model to study this problem, right?
Mhm.
So he's, in some sense, if you look at his paper, you have a feel that he has a global view of the whole problem. He knows it's very complicated, the whole problem.
Mhm.
But here's the essence of the problem that he proposes. Here, it seems that we're looking at sort of one little part of the problem.
Mhm.
So is it the right approach, really?
Well, I won't say it's the right approach. I think it's a right approach to the piece that it's looking at. Yeah.
I think if it were a control theorist to look at this problem, I don't think he would formulate it that way, right? Because he would be looking at the plant. There would be a plant, it's something to control, some objective function. He would not be looking at it this way.
Okay. Well, to try to address that, let me take a little bit of time out, which may leave you with yet another thing that you'll have to read that hasn't gotten described very much, to go a little bit into the history of why Massey introduced directed information. Massey was prompted to do that by looking at a paper in the Communication Transactions by Marco some many years earlier, in which Marco tried to build a communication model. It wasn't Shannon's communication model. It was different. And what happened in Marco's problem is that he tried to model, or was inspired by, in the modeling that he did, by trying to get at real-life communication systems in which there are lots of people, let's say, who are having a conversation like we're having here, and that what I say next is not what I had in my lecture next, but it's a function of how you and other people respond to it, who make responses to me in the meanwhile. And that I need to, so that all these people are feeding into one another, not in a big block long way where you wait to get the whole big block at the end, but continually in time. That there's the next thing that you put in and the next thing that I put in depend on what all of us did before. This is very different, and I think, than the usual channel model, that, especially the one that he had at first, that just had one transmission point and one receiving point and nothing coming back yet. Later on, he did look at two-way channels, and you know how hard that was already with one sender and one receiver. I guess we still don't know what the capacity of the region of the two-way channel is. And that was a memoryless two-way channel. So I guess what I'm trying to say here is that there is perhaps, when memory is present, a distinctions between the information that goes from one set of variables to another set of variables, in the way that Massey drew the arrow for it, as opposed to the information from that, as he defines it, from the second set of variables to the first set, which is not the same. And Massey's thing is not symmetric in X and Y. That's why it has direction. And there's a lot of this directed communication going on, and it's going on continuously. And yeah, maybe if you got some way to formulate that whole problem and try to solve it, then of course you should do that. And then it's further complicated by the fact that when you make the decisions, they go out into the world before they come back. So I guess, yeah, I'm certainly not trying to solve the whole problem because I think it's far too complicated. But I'm trying to do something to at least deal with a piece of what seems to be happening at the lower levels in primary cortex with the information that comes in. And that in itself is challenging enough, but I fully agree that it's not modeling everything of interest. It's not modeling the global problem. Okay. If you look, I don't have the reference with me to Marco's thing, but if you look in Jim Massey's papers, you'll find it there.
He was the predecessor.
Sometime in the.
He was the predecessor of Joachim Hagenauer. He was Joachim Hagenauer replaced Hans Marco at Technical University of Munich.
Yeah, that's correct.
The history.
Yeah. So this paper was sometime in the 60s or 70s. I think the 70s, early 70s, something around there. Yeah, and it wasn't in IT; it was in communications. All right, I'm going to see if I can get this thing to listen to me, and I know how to, I'm really having trouble with your system here because it doesn't show me the usual. You're going to have to come up here again and tell me how to get this out off and the other one on. Oh, and there, this escape button, not the mouse. Okay. So then I want to close that file and bring up the other one, which is D Laplace up there, the second one.
This is the one they have.
Okay, this is the one you have. This is the one that you have as a handout. At least I think that now everybody has a handout, or most everybody.
They should have it, yeah.
Can you keep it as big as it was? It was better the way it was before.
Oh, we could do it that way. The only thing is then you'll...
Or does it show up there the same thing? Oh.
Yeah, it will. But
I don't mind sliding down it. That's
okay,
fine.
If you
That's
don't mind
fine.
sliding
Okay.
down, that's okay.
Okay. That's a little better. Okay. Okay. With this last thing that I'm going to talk about is something that I've been working on quite recently, and I'm rather excited about it in several ways. So this is very definitely a preprint. It hasn't been shared with anybody but Chip Levy before this. And even this form of it was only shared with him a day before I came here. He knew what it was going to, a lot about what it was going to look like. So let's just talk about the title for a while. Bombardment intensity distribution in refractory primary cortex via Laplace transforms. Well, for this audience, at least I don't have to say what the Laplace transform is. That's because I can look out over the audience and say that fortunately you're all, or maybe I'm wrong, correct me if I'm wrong, you're all mid-20s or above. Good. And that means that if you went through electrical engineering, they didn't take the Laplace transform out of the damned undergraduate curriculum yet, which they're now trying to do with DSP first and all that stuff, trying to remove it. No, but after all, what was it good for? Lumped circuits with capacitors and inductors and things in it. The world doesn't have any of those anymore. We just had chips, so chips don't need a Laplace transform. They need maybe a Z transform, if that, but they certainly don't need a Laplace transform. Well, I think still need a Laplace transform, and I certainly made very good use of it here. Okay, that's that word. Distribution, so bombardment intensity. Well, that has to do with the picture that I drew before where there was this, but now it's just a single neuron. There's a single neuron, and coming into the single neuron are let us say, n equals 10,000 different input streams that consist of spikes. Spikes actually have duration of, have a certain shape to them, but let's, for the moment, consider that they're point processes, and that they're just coming in, and there's just a little point process coming in on each one of these lines every time that there's a spike. And their separate spikes are separated by some kind of stochastic point process, and there's as many as 10,000 of these stochastic point processes arriving to the neuron in continuous time. All right, although first we'll do this discretely in time, and then we'll talk about how you would move it to continuous. And that's the bombardment. And the intensity of the bombardment has to do with how many spikes per second are showing up, which of course is a time-varying random process. All right? If you call it lambda, then there's some lambda of t. You need, of course, to average over a certain interval of some duration in order to say what lambda of t is, because instantaneously it changes. But if you, well, I'll worry about that problem a little later on. But that's the idea of bombardment intensity. It has to do with kind of the arithmetic average of the number of spikes per second per neuron at time t that are coming in. Per neuron is afferent neuron that's sending one in. There's n of those, and I average up. I add them all up, and maybe I divide by n to average them, and that's the bombardment intensity normalized, or if you don't normalize it, it's the sum of all of them. Okay, primary cortexes, as I said before, say in the visual case, the first few lower levels of these regions, V sub I, where I is, let's say, less than or equal to 4 to make a guess. Refractory. Refractory means that neurons have a so-called refractory period, so that when they fire, they can't fire again for a certain length of time. Neurons are little people, and they're just like you are. You know, you do something and you can't necessarily do it immediately. You need a little bit of time to recover. There's lots of things in your life that are like that. I don't have to go and list them all. You know what they are. Little neurons are in there, are actually involved in all those processes too, most of them. And they have their refractory period. Things happen chemically after the action potential is generated that result in the fact that you can't send another one for, usually it's something on the order of 3 to perhaps as many as 5 milliseconds after. What do you mean that you can't? How does anybody know that you can't? Well, they don't know. They don't know anything about that. All they know is that they measured them and they never saw it happen sooner than a certain length of time, no matter how hard they bombarded them in experiments, which they could try to do. That seemed, so it's sort of known. I'm going to treat it in this paper as if there really is an absolute refractory period with a known duration that I call capital D. Not that I really believe that that's true. To some people who were here talking with me at the break, I erased the picture that I had on the board about thresholds, but I'll put it back on. And I'll make it as big as I can so that I hope you can see it. This is not as thick a chalk as I would have liked, but we'll do it. So this is time. And this is, let's say, volts. It's a certain kind of a volt, which is a so-called postsynaptic potential, which is what builds up inside the neuron as it responds to all these spikes when they come in. And they go across the synaptic cleft and some neurotransmitter gets pushed apart, and that produces inside on a membrane inside the axon hillock, not the axon itself, but it's at the spike generator part of the brain, a potential. And then this leaks off this membrane also, so if nothing more comes for a while, it'll start to go down, but if you get enough of them coming in, it'll keep going up. And if it gets above the threshold, then this firing happens. And then it resets itself in another refractory period. So what does the threshold look like? Well, the view is that there's some D, and the refractory, and the threshold, this is threshold curve. And the threshold is infinite for 0 to D. And then after D, if the postsynaptic potential maybe now can get up to the threshold because it isn't infinite, and if it does get up to the threshold at any time after D, then a spike will come out then. Well, this thing that builds up postsynaptic potential, not too surprisingly, is quite well modeled by a filtered Poisson process. That is to say that each one of these spikes, when you union them all together, the 10,000 spike trains that come in on the neurons, to the neuron, are well modeled by a Poisson process, the intensity of which at time t is the average of the intensities on the 10,000 lines, or the sum of them, let's say. Now let me say that every one of these lines that's coming in doesn't have a Poisson process on it, because it's a spike train from another neuron, and if that neuron, like this neuron, it's pretty much true in a given region, the one, and even for nearby regions, that if this guy's got refractory period D, so do most of his neighbors. And so they all certainly have refractory periods, even if it isn't the same D. And that means that after they make a spike, they can't make another spike for some length of time, which means that they're certainly not Poisson processes, because Poisson processes don't have a lower limit on the time between two successive spikes. But the neuron arrivals are asynchronous in real life. They're asynchronous. And therefore, as soon as there's two or more of them that are feeding into you, there is no lower limit any longer on the time between two successive spikes. And when you put this together, then you begin to see that it's not unreasonable to say that the union of all of them could be well modeled by a Poisson process, even though you didn't have a Poisson process on any one of the individual lines. This is an example, if you want the mathematical justification behind the fact that this is likely to be very Poisson looking, you have to go to Stein-Chen theory of so-called Poisson approximation, and I give some references to that. They do it first for random variables and then for random processes. powerful mathematical theorems that tell you some conditions under which a Poisson process approximates well some other sort of process, and how to measure the error between these things if you know enough about the pieces that are going together to make it. And I think it's a pretty safe assumption here that the thing is very well modeled, but not perfectly modeled by a Poisson process, but well enough for most of the things that I want to do. Why is it still not Poisson? Well, there's this consideration. Suppose that all the things that are feeding into this neuron that has refractory period D also have refractory period D. And there are n of them. Then the highest refiring input union, the total bombardment intensity summed from all of the input lines that you can sustain is n over D. N spikes per D seconds. Because if you try to get it up higher than that, if you try to send 2n in D seconds, then by the time that, or let's say if you try to send, 2n in D seconds, well, at some point along the way they're saying in the middle you've sent n already. And that means in the last D over 2 seconds, all n of them have fired, and therefore none of them could fire for at least another D over 2 seconds. So you can't do that. And so, yes, you can have two spikes that are as close together as you want. You could say that the intensity is, instantaneous intensity is as big as you want to make it at that moment, but you can't keep it up. So there's a distinction between sustainable intensity, bombardment intensity, and sort of an instantaneous bombardment intensity. But anyway, this thing is well modeled by a Poisson process modulo that comment. Okay. Did I get all the words? Bombardment intensity, distribution, refractory primary cone. Yeah, okay, I got all the words. Now, so what I'm trying to do here is to build a model for how the neuron responds to the Poisson process in order to determine when it's going to put out the next spike as a function of the intensity of what it has seen. And then, and this is going to be averaged not at this moment over the current, this distribution that I'm talking about is not going to be determined at this moment for the value of intensity that's coming in, but as intensity varies over time in the long run, what is the distribution of this time between spikes going to look like? But I don't need to use this theory to figure that out if I believe in the energy thing. And that's another paper that I'll put up on there, that one I have done. And that paper is somewhat in some sense related to the previous paper, but it's different. Says that in order to maximize the number of bits per second that is conveyed by the time between one spike and the next spike, subject to an energy constraint on the device that produces it, the time between spikes must in the long run have a distribution which is exponential. I don't mean at the moment right now in the next one and so forth, but if you look at a very long time and you look at all the spikes that this thing produced over hours or days, and which may be way up there in the hundreds of millions to billions, you look at all those spikes and all those intervals between them, and you put them into a thing and you look at the distribution. It has to be delayed exponential if it's energy efficient. It has to be an exponential distribution with a delay on it, and nothing else. It's a very beautiful result, by the way. And you get that first at a discrete time, and then you can push it to continuous time. That's how it has to be. And now, when I know that and I postulate a certain model, I'll tell you in a moment for how the input intensity versus time gets through this Poisson process that then gets filtered to build up the postsynaptic potential to cross the threshold, produces the thing that I'm after is, what is the distribution of the intensity? What is the long-run distribution of the intensity of the bombardment? What fraction of the time is the mean rate of arrival of spikes less than or equal to some number lambda? Lambda, let's say, is really n lambda, per arriving thing, lambda. I want to get the input spiking intensity distribution. That's the thing that's going to come out of this Laplace transform. But to do that, of course, I have to have some other things that I model. All right, well, this is the picture of what threshold looked like. when you build this Poisson process, depending on what at the moment, not now, not in the long run, but at the moment, what the bombardment intensity is, if it's very high, Campbell's theorem from shot noise or filtered Poisson processes tells you that there's some mean curve. It depends on how intense the bombardment is at the moment. And that's the mean value of this, if you will, shot noise buildup starting at 0. And of course it's Poisson, so that it doesn't really look like that, but it looks like this. And this one looks like this. And more to the point, this one looks like this. And this one has another realization that looks like that. And this one crosses the threshold way out here, and that one crosses the threshold way out here, even though they're both around the same mean. And when you do the mathematical analysis of this, you find out that except for the very highest levels of excitation that bring the curve up very fast through this fixed threshold, that the coefficient of variation, the standard deviation of the crossing time to the mean crossing time for all the intermediate and even lower ones that don't even get up there at all as far as their mean and require Poisson peaks to put them above, that coefficient of variation is 1 and worse, which is a disaster. It says that timing codes are impossible. Can't happen. So I derived that thing, and then I looked in literature, and I found that lots of other people had done that same sort of thing with much the same model I had done earlier. And it came to the same result, that there was very high, most of them got the same result, let's say, that there was high coefficient of variation. They didn't bother to try to tie that to timing codes, but they did point this out. And so when I got this, I said to my, my bio collaborator, I said, well, you know, if it doesn't make sense to me. It only works over here where I get very little, you know, maybe a little early or a little late that it crosses, or in this case it was just about the right time. But if this threshold curve came down like this, something like this, versus time, then all of these crossings would be nearly perpendicular. And even when the intensity was lower, the standard deviation wouldn't be so big. I said, could it possibly be that the threshold curve comes down? Here's the response from the neuroscientist. Yeah, it could be. It could come down. What? I said. He said, yeah, it could keep coming down. This is a guy who's been working in neuroscience all his life, very respected. I said, well, don't you know if it comes down or not? No, he said, we don't know that. We have no way of measuring that. We just know when it gets crossed. We don't even know what it is exactly. We just know that there's this thing that we call the threshold, and when the spike came out, it got crossed. Amazing. I mean, this is the way it is. So now I learned that in order to make these results right, you have to have a descending threshold. Well, even that turns out not to be so. Oh no, he says, not necessarily. The threshold could stay where it is. All we need to do is change the conductivity on the membrane. He says you have some conductance on the membrane that lets things leak off, and the less you make that conductance, the slower they leak off. So if you want the threshold to come down, you don't have to actually make the threshold come down. You can leave the neuron where it is, and then versus time, change the conductance of the membrane, and you'll have the same effect. So in biology, there's always 3 or 4 explanations for anything that could be, that you can postulate might be the case, and you just don't know. But I'm convinced that in one way or another, either it comes down, or you change the membrane conductance, or some combination of the two, so that this happens, so that these times are accurately not messed up badly by the Poisson thing. There's a very small coefficient of variation over a wide range of input intensities. Now, among other things, why that must be true is that it turns out that at every synapse, there are chemical clocks there that keep track of how long it's been since the last time a spike arrived at that synapse, and possibly in some cases even the one before that. I don't know quite what they do with it, but they do it. This thing that also leaks off versus time, when it happens, it gets packed with some chemical and it leaks off, and they know how long it is. No, I mean, I'm saying no. The information about it is there at each synapse. It's kept for a while. Why would you bother to do that if you didn't really need that time accurately? Though I must say I don't quite know what they do with it at that level, the synaptic level. Okay, so here I'm trying to do this paper. And so I consider a neuron a primary cortex that processes n excitatory synapses. This, by the way, is another simplification, because among the synapses are inhibitory synapses that give you an equivalent of having a negative spike come along, and they tend to be smaller in number, but very often very strong in the strength of the effective strength. And the inhibitory neurons sometimes connect to lots and lots of synapses, and their duration of their spike is maybe a little bit longer sometimes too. So that, but I guess that today is not the day to go into inhibition. So we'll just say that right now we have excitatory synapses. There are n of them. They really come about by having more than n and some that are inhibitory. Okay. Now assume that the arithmetic average of the firing rates of the n spike trains afferent to these synapses is a random process, which I call lambda of t, and it's measured in spikes per second, and it varies slowly with t. Here slowly means that lambda of t, I'm assuming here, and this is not really true either, but it's going to be assumed, that it scarcely changes between the time you put out one spike and when you put out the next spike. This is not always true, but it's often the case. Okay. But for some mathematical, more than mathematical simplicity, I guess I'm going to assume it. It hardly changes. What I'm going to do is, given a non-negative real number lambda, I want to find the long-term fraction of the time that lambda of t does not exceed the value lambda. And I'm going to give that a name. I'm going to call that f sub capital lambda of lambda. This name is not chosen, this notation is not chosen without malice or forethought. Because what this thing says is that, well, I say in the next sentence, our motivation for using that notation, f sub capital lambda of little lambda, is that if the random process lambda of t is ergodic, then we may consider that there exists a non-negative random variable lambda whose cumulative distribution function, f sub lambda, would be this. Because the time average and the statistical average would exist, and they would be the same in this. I'm looking for that distribution, the one that corresponds, whose cumulative distribution evaluated at little lambda corresponds to the long-run fraction of the time that the excitation intensity is little lambda or less. And I'm making believe that there's such a random variable. Although all that I really know is that there's a process with a time-varying lambda of t. And I don't know whether such random variable really exists. It would require some ergodic assumption from the mathematical point of view to justify that. But I make that assumption. And then what I do in the paper is I find the mathematical form of f sub lambda under certain assumptions that we consider to be neurobiologically sensible. We also find an upper bound on the Shannon mutual information rate between the process lambda t and the point process comprised of the instance at which the neuron in question produces its output spikes. So once you get this thing, then you can also do an information calculation rate, but that's actually easy. But this is the hard part, is to find what lambda t looks like. So how do I do that here? Let's see, I push this thing up here. So I'm going to define a bombardment intensity process, B of t, which is a counting process. Starts at t equals 0, which is the time at which this neuron that you're studying just spiked. And then B of t is the total number of spikes afferent to the neuron during the interval from 0 to t. In other words, this bombardment process, B of t, is the counting process of the union of all the n afferent spike trains in continuous time. Okay, that's page 1. There are only 6 pages. How do I move to the next one? I guess I go to pages, right? Page 2. Didn't quite do that one. I really am having trouble with this.